I'm Laura Bonnell, and this is the Living with Cystic Fibrosis podcast coming to you from Detroit. Please subscribe and even rate and comment on our podcasts when it moves you. I learn something new with every podcast, and I'm always inspired by the people that are showcased here. We don't give medical advice. You need to connect with your doctor for that. I hope that this Living with Cystic Fibrosis podcast educates you and sparks some volunteering or advocacy. The CF community needs people like you. Thanks to our sponsors, Viatris and Vertex, for their support. This podcast is one of the podcasts I am most excited about. We talk so much science, and it's interesting and wonderful, and you're going to enjoy it. Dr. Mitch Drumm earned his doctoral degree while in a lab with Dr. Francis Collins, the former director of the NIH, and at that time, in 1989, the pair co-discovered the gene that causes cystic fibrosis. The discovery of the gene that causes CF was one of the biggest contributors to science, even though science didn't move as fast as we wanted it to in 1989 or as fast as we thought it would move. It still moved pretty fast, so look where we are today with a modulator drug that corrects the underlying condition of CF and more possibilities in the pipeline. Dr. Drumm is one of those scientific heroes. He is currently a professor in the Department of Genetics and Genome Sciences, vice chair of the Translational Research, director of the Research Institute for Children's Health, and at the CF Clinic at CF Western Reserve University. Because of the success in cystic fibrosis, Dr. Drumm brought together faculty from across the Case Western Research University campus in 2015 to form the Research Institute for Children's Health. This institute was launched to implement laboratory-to-clinic research programs for other rare genetic disorders patterned after the CF approach. Dr. Drumm currently serves as the Institute's director, using it as an infrastructure for rare disease research, but also as a platform for community outreach. His current research in CF focuses on gene editing approaches to therapy, and he has active programs to understand altered metabolism in CF, problems of CF intestines, and how genes that modify CF disease severity convey their effects. He develops and uses mouse models to approach many of these questions, and we get to all of this. I'm really excited for you to hear what he has to say. Welcome, Dr. Mitch Drumm. Thank you so much. It's wonderful to have you on the Living with Cystic Fibrosis podcast.
Oh, thanks for having me, Laura.
And I feel like this is historic for the Bonnell Foundation because now I have two scientists, Dr. Francis Collins and you, both wonderful humans who brought the gene that causes cystic fibrosis to light. I mean, how amazing is that? Congrats again. I know it's been a while, but how cool.
Thanks. It has been a while, but it seems a little bit like yesterday.
I bet it does. And I said this to you before, the last time we spoke, that it's amazing and unbelievable that in my lifespan, I have seen the discovery of the gene and the scientists are still alive and well. Usually in disease, though, right? It's such a slow process that the heroes we want to meet are long gone. And this is in my lifetime and my daughter's lifetime. So it's really cool.
Yeah, it's amazing. I mean, it still has taken several decades to get us where we are, but it's moved faster than most any other disease research has, genetic disease research.
Can you take us back to that day, where you were in your career and then where you were in that lab when you discovered it?
Yes, and I have to put it in context. I don't think it's right to think of it as a eureka moment because it was little bits at a time. And even when we were pretty sure, we weren't positive that we had the gene. I was a graduate student at the time, so I had joined University of Michigan's Human Genetics Department in 1984 and had done a short rotation with Francis Collins in his lab. He had just arrived there as a new faculty member as well, so we were both starting at Michigan, about the same time. And he was looking for students to join his lab, and I was looking for a lab to join, and we hit it off pretty well with each other and agreed that after I finished all the obligatory rotations we had to do, that I'd come back to his lab, and I did. Then some events happened in life. Neighbors who had a boy born with cystic fibrosis. He was born the end of 1984, and I came back to Francis's lab in 1985 and was working on a technique to move along the genome. And the context of the time was that we didn't have a human genome project then. We didn't know what was where on all the chromosomes in our cells and things. So Francis Collins had devised an idea of how one might move more quickly along the chromosomes to get from point A to point B. Anyway, we got the technique working. Neighbors were born with CF, so I asked him, I said, hey, do you think I could try applying this to cystic fibrosis? And he said, yes. And about the same time, Lapchi Choi in Toronto at the Hospital for Sick Kids had found a variant in the genome that looked like it was tracking in families with cystic fibrosis. It wasn't the CF gene, but in order to track in those families, it meant it had to be close to the gene. And we didn't really have a good idea what close meant at the time, but it gave us a starting point. So, and I'm only giving you all the details here just to give you context of the time of this, but
I love the details.
So
it really paints a picture. It's very helpful.
So we Francis called Lapchi, and I think they also hit it off very well and agreed to collaborate on this. So we took the piece of DNA that Lapchi had, and we used it on our little technique we called chromosome jumping. And we started hopping along the chromosome, not knowing which chromosome at first. Turned out it was chromosome 7. And then, I won't even say fast forward, but move forward to 1989. And we found, as we were doing this jumping, we were looking for signatures of things that might tell you that a gene was in that area. And by today's standards, the technology was pretty crude, but there were signatures. And so we had a bunch of false starts of things that looked like they might be the right thing, but weren't. But then in 89, we found one that turned out to be the front end of the CF gene, this guy we call CFTR. So I sent my pieces of DNA to Toronto, and they looked at them to see how they corresponded to the DNAs they had from families and people with CF. And turned out that, like I said, that piece of DNA had the front end of the gene. And then we had to go through a number of other iterations to find out, well, is it turned on in the right cells? We know that this affects the lungs, the intestines, the pancreas, so on and so forth. So it looked like that gene fit the criteria. And then Lapchi had a colleague just down the hall named Jack Reardon, and Jack had created these things called cDNA libraries, and basically they were versions of all the genes that were expressed in turned on in a particular cell. And so he had one, a library from a CF patient, and when he looked at the gene and the DNA from that source, he saw there were 3 bases missing that weren't in the library from the non-CF source. He said, okay, that's something, but we still don't know if that's what's causing the disease and so on. So after some more tests, said, well, wait a minute, the only time we see that 3 base pair deletion is either in a cystic fibrosis patient or one of their parents. And that was what we were looking for. As geneticists, that's exactly what we're looking for. So anyway, so all the pieces started to come together as far as what it looked like. And then after we had done that, then we had put together a normal copy of the gene. This was in the early 90s now, but we took what we thought was a normal copy of the gene, put it back into CF cells that we could grow in culture. And when we did that, those cells regained their ability to transport chloride. And that was kind of the nail that really solidified it, and said, okay, this is definitely the right gene. And now we're where we are.
But even though I understand from what you're saying, as a scientist, it was a slow process, was there some jumping up and down and screaming? Because I would have been, I just think that would still be so exciting.
It was, and I'm speaking for myself, but I get a high out of every day I walk into the lab and we found something new. You don't know until you look backward how important what you found truly was. But yeah, I mean, we were excited. The CF Foundation had gotten involved with us right around when we started this project with LabG. And, you know, they were an incredible force to keep the motivation going and the excitement. I don't know what picture people paint of the laboratory scientists, but we, like everybody else, like to feel appreciated. So knowing that somebody cared about what we were doing, that was pretty important. So,
and I think that's really important to say, because now I think there's more interaction with parents and scientists and touring labs. But
yeah,
I can't imagine being in a lab all the time and not knowing how much you're appreciated by families. I'm glad that there's more interaction and thanking and speaking between the two groups. But we're not going to leave 1989 yet, because you and I talked, and serendipitous, whatever, our life paths were definitely, in my mind, predetermined, predestined, whatever you want to call it. Because at that time, that was the year I took off of news reporting and decided to go work for the United Way in Ann Arbor, the Washtenaw United Way. And that's when I was in the lab, because we were doing a newspaper insert about some of the agencies that the United Way supported, and one of them was cystic fibrosis. I wasn't married to my now husband, Joe, yet. We didn't know we were carriers of cystic fibrosis. I'm in the lab. I'm sure I met you back then, but, don't remember. It was a while ago. And that's when I was asking you, did you remember Jeff Pinard, who was the first person I ever met with cystic fibrosis? He was 24 years old and he was doing some lab work, and I met him. And of course, you remember Jeff.
Oh, very well. Yeah.
It's just unbelievable to me how paths cross and destiny, or wherever we're supposed to be in the world. And then, of course, I went back to radio and started doing stories about cystic fibrosis and trying to raise awareness once we had a child with CF. But that crossing of paths and that whole thing in my life before we even knew about CF is just incredible.
Well, and Laura, I want to follow up too on about talking with families, because I think it's crucial that we do that, because we need to make sure folks are aware we should be optimistic about what we can do, but we also have to be realistic about what we can do. And one of the things that came out of the 1989 discovery was folks started throwing dates at which it would make CF go away. And how those arose, I'm not sure, but it was a disservice, I think, to the community to think that in 2 years, 5 years, 10 years, we'd have it fixed. We knew we could fix it in a dish, but we didn't even know how the physiology of the disease was working at the time. So going out and telling people about how the research process works, not to make them understand all the nitty-gritty details and things, but to understand how incremental this process is. And, we get to watch the movies about how on Monday somebody finds something and Tuesday everything's all better. It just does not work that way. And we need to get out there and tell people what we do.
The reality. That is a huge and great point, because I can tell you when Molly was born in 1994 and Emily in 1997, we had so much anxiety about, well, they discovered the gene in 1989. We absolutely, as parents, felt that. The cure is like, and all of the doctors were saying, it's around the corner, like any day now. Like you did feel that. And in the CF clinics, we go every 3 months. And as you know, Dr. Samia Nasser will tell you after we did switch to U of M, but I started saying at every appointment, like, well, how long are they going to live? I need to know. Tell me, what's the year? Every 3 months I was asking, and every appointment I was crying. Like, I need to know, when's the cure? What's going on? I can't take it. Like I need to know.
Yeah.
So I think that's a really good point, because then I started thinking, well, there isn't going to be a cure in my kid's lifetime. I just need to wrap my head around that and live our lives, because there's not going to be a cure, and I can't just keep thinking about it every single day. So that is a really important thing to say. And then it doesn't mean you don't have hope. It doesn't mean
Correct.
You're not expecting and hoping for things to happen, but it's hugely important what you just said.
And we can't predict when the next wow moment's going to be. I think everybody's heard now of CRISPR-Cas. Well, before that was identified, there were some other techniques that looked like they might work for gene correction, but CRISPR-Cas has been a game changer. So when that's actually going to make it to clinical application in CF, I'm not sure, but I'm 99% sure it's going to.
Can you briefly describe that for people?
Yeah, sorry. So this was a discovery that came from folks working actually in bacteria, that bacteria have the ability to sort of their own kind of immune system, where they can, if they get infected by a virus, they've got an enzyme that'll chop up the viral DNA. So what some clever folks did, they said, well, I wonder if we put that enzyme into a human or other eukaryotic cell, if it could do the same thing. And lo and behold, it does. So what it did was it gave the ability to take that bacterial system and use it to find specific sequences on our chromosomes that we could cut. And that was just an ability we just didn't have before. So you can go in there, and the importance of that is if you can cut or break the DNA, then you can trick the repair process. So our DNA gets broken all the time. We're out in the sun, the UV light breaks it, and our cells have ways to repair it, bring it back together. But now when that break happens, we can trick it and have it copy from another piece of DNA what we want to be in there. So now imagine I can go into the CF gene, I can break it at the delta F508 mutation or whatever mutation someone has, and when that DNA repairs, I can trick it into putting the normal sequence, the non-disease sequence in there. So again, this was not even science fiction, just barely over a decade ago, and now we're using that technology right and left to repair. It's being used in sickle cell right now. People are exploring it in a lot of other genetic diseases as well.
And it's in the book Codebreaker, which is in front of me on my shelf. It was Dr. Jennifer Doudna, is that correct?
Doudna, yeah.
Doudna, thank you. Phenomenal book.
Yeah, and I think it's a wonderful example of why we need to do basic science for the sake of just understanding things, because she was not setting out to figure out, now, how can I edit the human genome? No, she's trying to understand how these darn bacteria and viruses interacted with each other. So anyhow, it's a wonderful story.
It is. And I wondered, did you think then that you would have learned what you've learned so far? And I mean, you probably never imagined you would be there discovering or co-founding the gene that causes CF.
I was going to be a veterinarian.
Really?
That was my life aspiration until graduate school happened, yeah.
Well, thank goodness you switched your career. I mean, for us anyway, this could even,
Well, it's funny. It's kind of a kismet thing. I'm allergic to most of the animals that I would have wanted to treat.
Wow. What is the most exciting thing for you to watch in the rare disease community as, science and everything changes?
I think it's the idea that we can fix these things. As a human geneticist, as we learn more and more about the genome, we could identify what was causing a particular disease. So that's important. I mean, people not knowing, as a parent, if your child's sick, not knowing is a horrible situation to be in. So at least we can help with the prognosis, or the diagnosis, I should say. But now we're at the next step where we say, okay, once we understand what's not working right, now we have a much better chance of fixing it. That for a lot of these disorders, even if they were accurately diagnosed, the only choice a doctor had was to try to treat the symptoms. Now we can try to get in there and fix the source of what's causing those symptoms. And using CF as an example, kids were treated with antibiotics chronically in most cases to try to keep the bacterial infections down, pancreatic enzymes to deal with the digestive problems, and so on and so forth. And now, knowing that we've got this darn CFTR molecule, that for many of these patients, the protein's just not making the right conformation. So the cell says, well, you don't look right to me. I'm going to degrade you, get rid of you. But the new modulator drugs, they get in there. We know what's wrong. And those drugs get in there and they allow the protein to form its correct structure and actually function. And to think that, there's probably somewhere between 10,000 other rare genetic diseases like this, that CF has really paved the pathway, the scientific pathway, but also the psychological pathway for hope that we can do this for most of them. I don't know if I can say all, but far more than we have done right now. So seeing that transition from understanding to intervening, that is truly exciting to me.
It is, and I think, like you touched on, also what we learned from CF will help other diseases, and that's just the way science works.
Yes.
Medications are used for multiple diseases, and it's very important because, as you know better than me, 95% of rare diseases don't have FDA-approved drugs. We're very lucky,
right,
in the CF world. How do you see that, and how do you see it changing?
Yeah, so rightly so, the processes for FDA approval of a drug, it has to go through, the first thing one worries about is doing more harm than good. And so they have to go through the safety trials to find out that there's not some bad effects of the drugs, figure out the dosages, the timing, and so on and so forth. And it's evolved that from those first trials that were done back in, I think, 2011, with the first modulator, now we understand that we can get enough information out of cells grown in a dish that drugs for CFTR anyway can get approved much more quickly than they could a decade ago. And I think that's an important concept because CF is rare, but it's not nearly as rare as many of these other disorders. And so to do clinical trials, typically you have to have a certain number of individuals to test the drugs on for those first pass. And if there's only 10 people on the planet who have it, how are you ever going to get that large patient base to test things? So coming up with surrogate ways to test them is important. And again, CF's kind of led the charge on that. They've also have something that most diseases don't have, and that is a CF Foundation. And the CF Foundation has the advocates that go to Washington and try to make sure that, I know you're well aware of this, that they're the ones who try to twist the arms of our government folks to help us out here. They engage in the social work. They work with the pharmaceutical industry, so on and so forth. And this is just not typical of most of the rare disease foundations. It's more typical that a family who has a child affected by something, they start their own little foundation. They want to raise some money and do good to get the research to get a treatment, but they don't have all those other arms because they don't have the size and the bandwidth. So I'm sorry I'm getting off topic, but...
No, I think everything you've said is really important. And I was just at a couple events and experienced exactly what you said. I met a mom who knows of 800 people with her son's disease, and they are struggling, and they're always looking for how do we get bigger? How do we get the word out there?
Yeah.
And then I just met a doctor, Dr. Caleb Bupp, who just discovered, do you know?
Michigan State, yeah.
Yes, yeah. And he just worked on medications for 12 patients. They just, these things are like incredible. So both ends of the scale, like everybody's working to try and figure out how to help different diseases.
Yeah.
And do you think that science and innovation, we took a hit during the last administration. It's the truth. It's not a political statement. It's just the way it was. Confidence, I think, took a dive. And do you think we can get it back? Do you think it's coming back? Do you think that just continued education will get more faith in people again?
I sure hope so. If not, I think we're in deep doo-doo. And that's another reason I think it's the scientists need to get out and talk to the public and separate fact from fiction. All the stuff that came out during COVID about vaccines and so on. Those of us who live this day to day, we just don't understand how people can be, misguided, put their head in the sand, whatever it is. How can you not be evidence-based in your thinking? I do hope we'll get it back. But we have to put people into office that are interested in the public and not themselves. And I'm trying to not get political on this, but we can't do witchcraft.
Right. I think you're 100% accurate. And yeah, it absolutely needs to. And on a different level, know it from a parent perspective, right? You know it from a scientific perspective. So yeah, when all that was happening, I did reach out to the administration and said, the CF community, we know about masking, like, please talk to us. No one ever answered me, but I did try. I was like, we can talk to this. We can tell you about this. So yeah, I agree with you. We have to put really smart people in politics because it impacts all of us. Right now, we're dealing with the Rare Disease Advisory Council, trying to get that going, the dangers of the Prescription Drug Advisory Board, on and on, Orphan Cures Act, all kinds of stuff. So it's really important. And that's actually, I'm so glad you mentioned it because that's what we're talking to doctors about. You need to know about what's going on in legislation.
And not just the science. The economics are huge in this area too, right? You know what the price of the CF drugs are, and if all of the 7,000 to 10,000 diseases had new drugs that all cost the same amount, our healthcare system would collapse. So it has to be a multidisciplinary approach to all of these things as well.
And I think not this specific drug that Caleb Bupp just was dealing with for these 12 patients, but it's millions of dollars per person.
Per person, exactly.
If you're just talking about 12 patients.
Yeah.
But isn't everyone's life worth it? Right? So we have to figure it out.
Yeah, sorry. Now I got 10 different things on my
well,
mind
say
to talk
any
about.
of them. That's fine. What were you thinking?
No, just Caleb's incredible findings and application. I'm hoping there are hundreds more of those stories out there that I don't know about. But in terms of the fundraising that's needed to do the research is just inherently expensive. The instruments now are so much better than they were 10, 20 years ago, but they're also way, way, way more expensive. And so when the individual families start their foundations, there was a time when $5,000 or $10,000 might be able to move the needle a little bit, but that's rare that's going to happen anymore. So finding ways where people can pool their resources. So imagine a neurological disorder that's really, really rare, but there's 50 other ones that are very similar but have a slightly different cause. If all those folks are able to come together and pool those resources, now they can invest in something that actually might make a difference. And I understand wanting to be solely focused on your child and things, but I'm hoping there are ways we can bring people together to sort of, fight a common enemy.
And I think you're correct, because if we only focus on CF or one disease, that really limits us.
Absolutely.
I think it's really important that you're looking at the big picture. It's never for us. I think it's safe to say that being so narrow-minded on one disease is not benefiting anyone. It's really important to say, hey, I want to help you, or here's what we found. Or even as a CF parent, just talking to other rare disease parents, we all go through the same thing, and everybody can share information that benefits all of us. So I think it's a really important point.
I'll give you one example. So my mentor, Francis Collins, as he went on to the NIH and headed up the Human Genome Project, to get that first genome sequence was $3 billion, took about 13 years. Now I can walk down the hall to our genome core, and for less than $1,000 in 24 hours, I can get an entire genome sequenced. Okay.
Wow.
And that genome that I'm sequencing, it doesn't care what disease I'm looking for. It will do any of them. So you have a machine like that or an instrument like that that can be used for any purposes. Why wouldn't you want to put your funds together to support something like that? Anyway, that's my soapbox.
It's a great soapbox because it will help all of us globally.
Yeah.
And different challenges in low-income countries don't have access and don't have the ability. So whoever does, as they say, it's up to those who have, who should benefit everyone. I didn't say it as eloquently as this, whatever that terminology is, but it's up to everybody who can. What do you tell young doctors or even young families who are just coming into cystic fibrosis or the rare community? Because things have changed so much, but it's important for young doctors to know the history of how rough CF was and can still be.
Since I'm not a physician, I don't see the patients, but I do talk to the doctors a fair amount. I think one of the benefits at our place here, the Children's Hospital is 50 feet away from me, so I get to talk to my clinical colleagues fairly regularly. Yeah, Laura, I don't know the answer.
That's okay.
Yeah, the disease going away is a good thing, but as you well know, it's kind of now there's two different CF diseases. One is those who can benefit from the modulators and those who can't.
Right.
So we have a small but very significant population who are not benefiting from these new wonder drugs.
Do you think that status will change? I know there's so much work being done, and Emily's entourage is working diligently on finding, new modulators for that 10% of the population that can't go on Trikafta. There is a lot in the pipeline, but what are your hopes and thoughts on that?
Well, this is where I really think the gene editing can be the difference maker. So the type of mutation Emily's entourage is focused on are the ones that don't make any CFTR protein, so there's nothing for those drugs to act on. So I think they're the only, I shouldn't say the only, I'll be proven wrong, but the most likely hope is that we can get into those cells and actually fix the gene itself to allow it to make protein, and not just protein that the drugs can act on, but proteins that don't need the drugs, so that would be a totally normal CFTR. I think we're moving so fast in that area. That's, if I had to look in my crystal ball, that's where we're going to make the next big leap.
And what do you see? Like some more of that crystal ball or your hope. What is your hope for the future, and kind of what do you see on the horizon that is hopeful?
People are clever, and they come up with new ideas all the time. And, a lot of them, you do this kind of thing and say, wow. So I think with all the different people working on this, coming at it from different angles, so there are a bunch of us who are trying to figure out how to get into a cell and fix it while it's in the body. There are other folks saying, well, we can do this a lot more efficiently if we take the cells out, fix them, and put them back in. That's not something I thought was going to be realistic, but boy, there are data coming out that say, no, it looks like we can. We can get into what are called the stem cells, get them to, what it's called, engraft into the tissue and things. So I think it could be one, it could be multiple of these things that are going to pan out first. Right now, our biggest challenge is getting enough cells fixed to make a difference. We know we can do. If I take the cells, put them in a dish, grow them in the lab, I can fix them 7 days a week. But if I have to go into the person's body, how do I get the machinery to do the editing into all the different cells that need to be fixed? And that's our big hurdle right now. But there are a lot of people working on different ways to do that. Some are using viruses where you take out the guts of the virus so it's not pathogenic, but you can replace it with your editors and things to get them into the cells. Viruses are very efficient at getting into our cells, but the logistical problem there is once you get a viral infection, your immune system says, I'm not going to let that happen again. So how do you set this up so that you can repeat the administrations more than once? There are folks working on chemistries called liposomes and little particles that if you get them into the bloodstream or in contact with the cells, they fuse with the cell and will allow that machinery to get into them as well. And a bunch of other chemistries that people are trying out. So I know we're going to hit on something. I just don't know which one, who's going to win, or if there'll be multiple winners and when that's going to happen. And this is one where it could very well come from another disease, whereas, with CF, we've got the whole body we have to worry about because every organ system's affected. Mm-hmm. There may be other ones where it's just the liver, just the brain, so on and so forth, where maybe they'll find the key because they have a more focused approach to take, and we'll learn from them. So,
well, you've been at this for, 30 plus years, right? I don't know exactly how.
It will be 40 years next year. Yeah.
40 years. So what else are you working on, or do you want to talk about or mention that you're doing that we can tell people about?
I think maybe two things. One is, as we've alluded to, CF has set the path. So we've started a small rare disease program here to do exactly that. The bottleneck now is not finding the gene like it was back in '89. Now, with the whole genome sequencing and the whole genome available, we know what the cause of most genetic diseases are, or we can figure them out pretty quickly. So now the next step is understanding the physiology and how that gene is causing the disease and trying to move that understanding then into a therapy. CF has caused us to have one focus is metabolism. As you well know, traditionally CF kids would be prescribed a super high calorie diet to try to keep their energy stores up. Well, that led us into looking at some metabolic disorders. the lung, the pulmonary involvements caused us to look at some other pulmonary diseases, some other GI diseases, things like that, where all the tools that we built for CF, we can apply to these other diseases as well. So that's one. The other one is, as I mentioned, we're really, to me, the tough nut we have to crack is how do we deliver these genome editing tools to the cells? And for that, we've engineered some mouse models that it sounds kind of Frankensteinish, but we put into the animals a gene from firefly that will light up. So rather than having a different outcome for every single disease, if we fix a particular gene, it'll cause those cells to light up. And that's something that doesn't take ultra sophisticated technology to do. So now we have one output system that will work for 7,000 different diseases. So trying to make those systems, and the mouse these are not harming the animals in any way. They are fine. But now we have the ability, because we have one of the world's best mouse engineers here on our campus, so we now can create tools that, even if I don't understand those other diseases, we can ship off the mice for any lab on the planet to use for their applications as well. So again, it's just CF has allowed a lot of things to happen.
It is really cool. My mind just spins and goes in a million different directions when you're talking, because I love the possibility and the hope for the future. I mean, can you even imagine what the future holds? I mean, I have so much hope, but I don't know.
No, I don't. I think as our diagnostics get better, when you go to the doctor and tell them you have an ache and a pain or whatever, they say, well, anybody else in your family have those aches and pains? And they're kind of asking a genetic question, but don't really do much with it. But pretty soon, I think, with the cost of genome sequencing coming down, you're going to have that information as part of your medical chart. And now when the physician asks that question, they can go back and look and see, well, wait a minute, who else in your family might have that as well? So it means that we're then going to be able to predict what might happen. So there might be treatments, interventions that can happen much earlier. With CF and lots of other genetic diseases, the longer it goes on, the worse it gets. So the earlier we can get in and intervene, the better. So I think those types of things are going to change in medical practice, probably slowly, but eventually they'll take place.
Well, thanks for all you do for the rare disease world, the CF world, and all you continue to do, because we need people like you. It's really important. Don't retire anytime soon. Selfishly, I'm asking. But thank you so much for doing what you're doing.
Well, thank you for having me. This was a fun conversation.
Yeah, we could do more. We could do part 2.
Okay.
This may not be the end. I mean, it's not the end. There's so much more to talk about.
We'll get to talk more very soon.
Absolutely.
The original music in this podcast is performed by Kevin Allen.
It's not complicated.
Who happens to have cystic fibrosis.
We all got our worries and fears. I know it's got you frustrated, but loving you is so alright.
This has been the Living with Cystic Fibrosis podcast. For more information and to learn more about the Bonnell Foundation, visit our website at thebonnellfoundation.org. That's the BONNELL Foundation.org. This podcast was sponsored by Vertex Pharmaceutical, The Science of Possibility, and Viatris. It was produced by Jag and Detroit Podcasts. Follow our show in Apple Podcasts, Spotify, or wherever you're listening right now.